The title of this talk is How I Learned to Stop Worrying and Love Atomic, but the message of this talk is you should never stop worrying. Distributed systems are hard. You should always keep worrying. You can love Atomic. Atomic is pretty great. It's about the fundamentals of database integrity and how to deal with concurrency in Django. Some quick background on me. My name is Nick. I work at a company called Monadical. We build a poker platform that's web first. It uses django-channels. We've been working on this for about 2 years, and we're hiring. Big red disclaimer, I am not a distributed systems expert. I cannot tell you how to design your distributed systems. You need to hire very, very expensive people for that. I just think that they're neat, and I've made a lot of mistakes along the way. So here are some solutions to some possible problems that you may encounter. So it all starts with a single slice of salami. I don't know how many of you remember the plot of Superman 3, but in it there's an accountant, and he gets his paycheck one month, and he notices it's like $144.22. And he's like, because he knows that his salary is an odd number, or a number that when divided by 12 is going to have some more decimal places after the 22 cents. And he's like, where do all those fractional cents go? What happens? And so he writes a program that collects all of the fractional cents that don't get given to people with their salaries, and he gets like $300,000. But of course, by the end of the movie, he gets caught. And the same thing happens in Office Space, and the same thing happens in Hackers. So this is a very common problem, and it's kind of like the intro to the problems that lie ahead when you try to deal with money and critical data where the numbers are important. So math is hard in general when dealing with money. Try not to do math whenever possible. Salami slicing is a little bit tricky because it happens when you don't expect. So it's not something that just because you know about, you're going to easily avoid it. You actually have to look out for it. And that's in places like decimal field, when you have decimal places equals 2. When you put a decimal that has longer decimal places into the decimal field, it may silently truncate them. And so you need to know what's going to happen to those subsequent decimal places. Also, don't try this. Accountants know how to catch this these days. You may be tempted. This is super basic. I'm going to go through it pretty fast. Don't use float, use decimal. Float has, it's not precise, and there's error that can accumulate. There are some cases where it's OK, but you need to know exactly when those cases are good. Python 3. I like to call this bonkers rounding, but it's actually called bankers rounding. If you're from Europe, this is familiar. If you're from the US, this is absolutely nuts. If you round 2.5 in Python 3, it rounds to 2, not 3. So anything on the half mark will get rounded down to the nearest even number. I just found this out like a week ago, and it's super surprising. If you want the behavior that you expect in the US, you can use decimal.quantize. So kind of one of the big themes of this talk is that concurrency is really, really hard. So whenever possible, we should try and actually avoid concurrency. And there are some things you can do. There's some strategies you can take to get rid of concurrency in your distributed systems. So first of all, what is a distributed system? It turns out every Django app is a distributed system. If you run Django, even on a single server, as long as you have more than one USG worker, that means more than one process, every single app is a distributed system. So whether you like it or not, you're going to have to learn some of the theory behind distributed systems in order to do transactions safely in Django. So what happens when two of these workers try to do an operation at the same time? If you're a bank, something very, very bad happens. Even if you're not a bank, bad things can happen. So let's take the simple example where we are a bank and we have a balance for each user. 2 threads, they are both working, and they both get a request at the same time. This user wants to withdraw $100. So they both check. Does the user have $100? Well, they both assume the user has $100. Then they both move on to the next step. They both remove $100 from the account. And then they both save $0 are left in the account. The user gets $200 when they initially started with $100. And at the end, the account has $0 instead of negative 100. This is a very simple example. It's also very, very easy to do this in Django. All of the docs have things like this in them. So if you're just reading through the docs and implementing stuff, you're going to run into this problem. And this is called a talk-to bug. I don't really know how to pronounce that, but it's time of check to time of use. We are a poker site, so we have to deal with this problem all the time. If a user has 2 tabs open and they hit fold on one and bet on the other, we can't accept both bet and fold. They might win $1 bajillion. So we have to be very careful to actually make sure that all of the actions are strictly ordered. And that's the solution to concurrency. 90% of the time is actually get rid of it. What you can do is you can use a queue. So every important operation that comes in you attach a timestamp on it, you put it in a queue, and then you have one process, a single process. Not one process per server, just one process on one server somewhere that reads off the queue and performs each operation. So this is a generalized solution that works for a lot of different things. So let's take the banker example again. If someone wants to check whether they can deposit or withdraw, you can make a banker service, and every operation that touches money, you take a timestamp and a condition and an action, and you put it all in a queue, and then you have one worker process read off the queue and perform each thing. If only one change can happen at a time for your table or your given models, no conflicting writes can occur. And the if statement and that talk to bug won't happen. So an example of how you can implement this in Django is to use like Redis queue or Dramatic or Celery. I highly recommend Dramatic. It has some great distributed systems properties. Not too many people have heard of it, but it's a fantastic alternative to Celery. It's thoroughly tested. One thing you have to be careful is don't let any other processes touch the same tables that your queue is doing as it runs through. But the end result is the same. You get a nice linearized order of transactions. So eliminate concurrency at all costs. Don't even touch it. You don't have to watch the rest of this talk if that's enough for you. Just get up and go, I won't be offended. However, that's not always possible. So many of you are going to deal with apps that are quite large, that have more than 1,000 users. And once you get to that point, you really are going to start having to think about concurrency. And here be dragons, so beware. We're going to talk about the basic tools that the ORM provides. Atomic transactions, locking, and compare and swaps. Locking is known as pessimistic concurrency. Compare and swaps are known as optimistic concurrency. And there are lots of models that use combinations of the two. I'm going to run through this quickly because I kind of assume some background knowledge with the ORM. Atomic transactions, basically you can make a bunch of changes inside an atomic transaction. If any of them fail, or if any exception is thrown, they all get rolled back, and none of them get committed. Transactions can also be nested, which is cool. That's fairly advanced. You'll know when you need it. Row locking. This is great. This is a very simple way to deal with concurrency. Basically, to prevent the talk to bug, before you do the if statement, you lock the row, which means that any other process that wants to modify this has to obtain a lock. And in order for them to obtain a lock, they have to wait for this lock to be released. And the lock is released at the end of the transaction. So basically, if you're a bank, you lock the user balance row, you perform your operations on it and any of the other rows you need to touch. The transaction completes atomically. It all either completes or fails. The lock is released, and then the next process can do something. So this is a pretty simple approach. It works a lot of the time. OK, so that was pessimistic concurrency. This is optimistic concurrency. The reason they're called that is because in pessimistic concurrency, you assume that other processes are trying to compete with you. You assume that someone else is going to try and write at the same time. Optimistic is the opposite. You assume that actually you're the only one writing, and you only fail when it turns out that that assumption is wrong. So in optimistic concurrency, one way to implement that is you save a version, or a timestamp, or something that changes every time the model is changed. And you read it before you run your logic, and then you run your logic, and then when you perform the update, it actually all needs to be a single line. It needs to be one statement that the SQL can operate atomically. And what that means is it'll check the version. For the rows where the version is what we expected, meaning no other processes modified it before us, it will perform the update. If no rows have that version that we expected, no update will be performed, and you're safe. However, this is really, really hard to get right. It's very easy to get wrong. There are a lot of ways in which you can read a version, another process can perform an operation, and then either the version check has some error, or maybe it's not actually a version. Maybe you're just checking the value. That's one thing to try not to do. Don't just check that the balance is what you expect, because another process could have come in, subtracted money. Another process could have come in and added the money, and then the balance looks the same when actually the rows changed. So versioning is hard. Compare and swaps are very useful, but it's hard to do this properly. So be careful. A cool solution is a hybrid of the two. So this is great because it gets the benefits of both worlds. You don't have to lock for all of your logic. What if you have to do something expensive when you have to read out of a file or something like that? You don't want to lock all of the rows while you're doing that expensive operation. So what you can do is you can get the version of the rows, do your logic, then only for the write phase where you're actually going to commit all the changes, check to see if the version was changed. If it wasn't, obtain a lock. Then once you have the lock, you can perform operations on multiple rows. You can get a lock on a whole set of rows or a whole set of models. You can do your complex write logic, and then you can save it. So this is kind of a hybrid solution, and there are not too many articles out there that give tutorials on this. Usually they say either do one or the other. But the hybrid solution is actually easier and faster in a lot of cases. This is actually used inside of Postgres. They use a write-ahead log, which is not actually log-structured data. It's something similar. But the cool thing with a write-ahead log is that if you read the version at a certain point of time, nobody else can change that row. Any subsequent changes are added as new rows in the write-ahead log. And so Postgres can make some assumptions about the safety of the data and can use a hybrid solution very efficiently. I won't go too much into that, but just know that it's used by a lot of things internally, and it's quite fast and useful. So let's talk about laying out your database to minimize locking and in order to be able to sleep soundly at night. So first, let's start with log-structured data. If you haven't heard of log-structured data before, it's basically a different approach to storing information. So let's start with a basic example of our bank. A bank, let's say, has a balance for each of their users. Alice and Bob. Alice has $52 and Bob has 21. When the bank wants to subtract some money, they go to the row that says Alice, they take 52, and they subtract $2 and they get 50, and then they save that. So that's the normal mutable example. Log-structured data, or log-structured storage, takes a different approach. So instead of storing a balance for each user, they have one big table of all of the transfers that have occurred. Every user starts with $0 in their account. To get the balance of any user, you run through the entire table and you add up all of their credits and debits. And then the total is going to be the balance for the user. And the great thing about this is that it's immutable. Any row that's added can never be changed. To change the balance of a user, you add a new row. And that way, you can rest soundly knowing that all the data before the current point in time will never change. It'll always be the same. And this means you can have multiple machines running. They can all be taking logs, and then you can merge them at the end of the night. And as long as you don't have conflicting timestamps, all of the operations will be strictly ordered. That's a great property to have in a distributed system. Strict ordering depends on having good clocks. So don't do this on commodity systems unless you have an atomic clock. Or at least know exactly what the possible collision cases are for timestamps. So log-structured storage in general is one of the foundational building blocks of distributed systems. And it's great to understand log-structured data and to be comfortable with it because it's a fantastic solution to a lot of cases where you have some mutable state and multiple processes are trying to mutate that state. So it provides that strict ordering of writes. It's immutable, another great property, and you can revert to any point in time. And a great example of that is Redux. So Redux is more of a front-end thing, but if you've used it, you know that there's a state that looks like it's mutable, but actually it's not mutable. What happens is events are added into a queue, the events are processed, and the state is transformed from one version to the next version. And you can roll back to any point in time because each one of those transformations is purely functional. CouchDB also uses log structure. Redis, if you turn on persistency, you'll notice it's an append-only log on the disk. That's another example of log structured data. However, if you try and do a log structure in SQL, you're going to run into a problem. If you're a bank and you have a balance transfer table, for every transfer that occurs, if you're reading some balance and you want to make sure that no one else is modifying that balance while you do some logic, what do you lock? What row do you lock? You can't lock a single row. You actually have to lock the entire table. And what happens when you lock the entire table? None of your customers can do any transactions. So locking log structured data in SQL is actually quite difficult because you can't, conditional locks are not readily available in Django. You can't say, if this row is added, don't allow this row to be added. That system doesn't exist. So how can we prevent concurrent writes when we use log structured data in SQL? We can create a separate row that is the lock. And this row actually doesn't have to contain anything. All it does is it serves as a lock, the designated lock, if you want to modify the balance for a specific user. In our case, I'm going to show this row contains the total for the user, all of their balance added up. And the reason that's useful is so you don't have to scan the entire table every time you want to get their balance. And so in our example, what we're going to do is we're going to create a user balance model separate from the balance transfer model. And we're going to require that anyone who adds or subtracts balance for the user obtains a lock on their balance total first. So I'm just going to run through this example really fast. We want to send money from one user to another. We first obtain a lock on both of their total balances. We check that there's enough money to send. Then we create the balance transfer object, and then we update. So the balance transfer is the log structure thing, and then we update the mutable total for both. And all of this is atomic. So it will either all succeed or it will all fail. And the side benefit is that you don't have to scan the whole table every time you want to get the balance. So to summarize, log structured data is great. You have to think very carefully about logging, and you also have to think very carefully about how you get aggregate data. So if you want to get the sum before a certain date or stuff like that, you might have to deal with caching, and that's difficult. I'm not going to go into that. So let's talk a little bit about the bigger picture. When you deal with a distributed system, there are a lot of other concerns. And especially if you get to the scale that you become distributed, there are a lot of things outside of the actual technical code that you're going to have to think about. One of them is a human issue. How do you structure how humans review and test the code and understand it? And one of the possible solutions is that you actually have all of your rights in a single place. So I saw an interesting talk yesterday about structuring your APIs and also an approach in Django that you can use that sort of is a different model than Django usually teaches, but it produces some interface to some models, and then all the changes to interact with those models are via the interface. I'm not proposing something so complicated. This is more of a very simple solution. So what I'm proposing is that put all of your rights to your core models in one file. Call it transactions.py. Now anyone that touches those core models is not allowed to update the models directly. And this is a human thing. You have to tell your developers, don't .save on models, don't .update on these models. If you want to interact with these models, you must import a function, a tested, small, contained function from transactions.py, and you must use that function. Because those are the functions that we pay our distributed systems guy $200,000 to review. And so if you're touching the models via some other method, that's bad. Use these functions. So this is just a simple way to think about how to separate the rights from your view logic and to have them testable and reviewable separately from the rest of your code base. Another thing to think about is that the database is not a magic genie that stores all data safely forever. Bit flips happen. Someone runs, MCX butterflies in their Emacs console. Butterfly flaps its wings 200 miles away. A cosmic ray lands on your hard drive, and a bit is flipped. So this actually happens all the time. Bit flips are regular. On production servers, there's probably a bit flip every day or more. If you Google how frequent are bit flips, you may be surprised. So solutions to bit flips: ECC RAM. ECC RAM is great. It's a form of checksummed RAM, and you can also get a checksum file system like ZFS or BTRFS. If you don't know what those are, they're amazing. ZFS is fantastic. I highly recommend it. But really, the panacea to these problems is backups, offsite backups. I'm just going to say this word 5 times. Backups, 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 backups. It's extremely important that you have offsite backups. Almost every postmortem that you'll read gets 10 times worse when the engineer realizes that they don't have backups. I heard yesterday that the Python wiki was deleted in its entirety by accident, and they had to recover the entire thing from Google caches. You don't want to be in that position. So set up offsite backups. If you learn one thing from this talk, it's that backups are the only thing. It's like the most important thing. And one thing to think about is maybe have your backups in a different format from your database. If you are a bank and you're storing balance transfers, maybe store all of your balance transfers in a JSON file as well as your database. Because if one of those has some fundamental integrity problem, it's always nice to be able to replay your data and recover it from a different data format. And you want to verify that the two are consistent. But if you have that, it provides some peace of mind. One way to do that is with streaming replication. Postgres has an option where you stream, and MySQL, of course, has this too, where you have a primary and a replica, and you stream all the updates over time to the replica. If the primary fails, you can fail over. Yeah, I assume if you've worked with large Django databases, you've had to deal with primaries and replicas. Another thing to talk about that I can't go into too much detail for, because it's 20 talks on its own, is database isolation levels. If you're dealing with a SQL database, this is something you're going to have to think about at some point. And that is, in some modes, SQL databases can leak partially committed data in transactions to other threads. And the exact semantics around when that happens are very complicated. I won't go into too much detail. But basically, the database can choose, or you can choose to have your database provide a very strong guarantee that all transactions are atomic and linearized, such that any transaction that occurs happens either before or after another transaction. No two transactions can happen at the same time, according to SQL. That's a very, very strict guarantee. You likely can't run with that guarantee because it's expensive. Otherwise, all databases would have this turned on by default. So you'll have to think about whether you want serializable, linearizable. Your database will probably support different modes, and you're going to have to read about those modes and think about it. A great person to look up is Afer. He wrote the Jepsen tests, which are the standard suite of tests for distributed systems. It doesn't just apply to SQL. It's a great set of tests to learn about. One thing that you may not know with Django is that it's possible to use separate databases for different things. And these databases can be entirely different technologies. So you could have one database that's on Spanner and one that's a MySQL locally. And so if your user profile picture is not super important to keep concurrent safe, you can have that in a normal database, and then you can have your banking database with a much higher isolation level. So the way to do that in Django is with nested transactions. And your transaction specifies which database it is, and any exception in any part of the transaction will roll back all of the transactions that are above that nesting level. So that's great. Multiple database transactions is awesome. That's extremely difficult to do in other code bases, but Django gives it to us for free. So now I want to go over a little bit of what does the future of databases kind of look like? What is in the space? What are the options? And there's been some really exciting tech in the last 5, 10 years. Great consensus algorithms like Paxos and Raft have come out. If you want to learn about consensus algorithms, check out Raft. It's great. The average developer can work through it and eventually understand it. It's very complicated, but it's easy to approach. And what Raft does is it allows us to elect a leader in a cluster of data storage engines. And that leader then can take writes and stream it to the rest of them. But not only that, any database in your cluster can perform queries. So it's no longer a primary replica situation. It's actually a cluster of databases where each database has an equal footing. So Google built something called Spanner based on this. And Spanner is their globally distributed SQL database built with atomic clocks. And a couple engineers in Google were thinking, and they're like, shouldn't everyone have access to Spanner? So they quit Google, and they started a company called Cockroachdb. Cockroachdb doesn't need atomic clocks, but it uses the same system as Spanner. It's a globally distributed new SQL database where you can perform SQL queries on any node, and they all replicate the changes to each other, and they support failover. So if one node fails, as long as you have like 3 or more, other nodes will take care of it. Now, another company came along, and they're called TiDB. TiDB is really cool. They're a Chinese company. They did essentially something very similar to Spanner, except they built a key value store first. The key value store is based on the consensus algorithm, and that's in Rust. So it's really, really fast. It's faster than Cockroachdb. And then they built a new SQL engine on top of their key value store. And the new SQL engine is in Go, very similar to Cockroachdb. And something great is they both work in Python. So if you want to think about potentially scaling or storing your data on different parts of the planet and having a fault-tolerant system, you can look at both of these. Unfortunately, I have to say they don't work natively in Django. They mimic Postgres, but they don't implement all of the Postgres features. I urge you all to go and comment and open issues saying this doesn't work in Django. Please get it working in Django, because the more people that ask, the sooner we'll get Cockroachdb and TiDB on Django. So the key takeaways from this talk. Don't use floats unless you know what you're doing. Use decimal. Don't use round. If you must, know exactly what the rounding behavior is going to be and make sure it's what you expect. Don't do concurrency. Just don't. Put everything in a queue. Do it one by one in a single process. Our whole code base on the Poker site is built on single processes handling everything. For every table on our site, Poker has tables and players sit at a table and perform actions. Every table on our site is a different process. And only that process can touch the models relevant to that table. So when 5 users all submit, post, fold, call, all of these different actions, it all goes into a Redis queue. And we have a system called a heartbeat that pulls it off the Redis queue and executes it in a single process with a lock on that table. And this saves us so much headache. We don't even have to deal with distributed systems. Everything is singly ordered. And if that process detects anyone else trying to touch the table, you can do this in Python easily with a version system. It throws a massive error, and it stops the entire code base. And luckily, that's never happened. So we can sleep a little bit more soundly at night. But don't stop worrying. Distributed systems are hard. Atomic is good. An approach to distributed systems is to lock dependent rows or use a hybrid approach with compare and swap. I want to give some special thanks to everyone who's contributed to Django. You're awesome. You've made this platform great. Also give a shout out to Andrew Godwin, who took the time to rewrite the Django ORM to support async. That's an incredible feat. If you've ever worked in Django and then worked in Tornado, it's like going back to the dark ages. There's the level of ORM support that SQLAlchemy gives is different. It's a different taste and flavor. I won't say it's better or worse, but it takes some getting used to. And the ability to use the Django ORM separately from Django. You can use the Django ORM in Tornado, in Flask, in anything you want. But now it supports async. So you can use all of those fancy frameworks out there that use async. I also want to thank Tyler Neely, who initially got me into distributed systems. And the final disclaimer, I'm not a distributed systems expert. These are only some tools that you can use to approach the space. And my company is hiring. Monadical is hiring. We're fully remote. We're based in Colombia. We'll fly you there for the first month to train you. Colombia is beautiful. It's sunny. It's a tech heaven. It's like a nomad headquarters. And I'm the Squash on Twitter. You can ping me for corrections or just holler and say you're wrong. Thanks.